Good morning, everybody, and welcome to the Centre for Applied Climate Sciences seminar series for 2022. Today we have Professor Jacky Croke from the University College Dublin presenting on the topic of using palaeoclimate data to better inform hydroclimate variability and the benefits to the water industry. My name is Kate Reardon-Smith and I'm one of the research fellows here at the Centre for Applied Climate Sciences. Our centre is based at the University of Southern Queensland. We have approximately 22 staff in Southeast Queensland, Melbourne and the UK. We conduct research including into extension, monitoring, evaluation and adoption to help people manage some of the risks they face from climate variability and climate change and to benefit from associated opportunities. We also employ a network of 16 climate mates located right across Northern Australia who act as champions in the use of meteorological and climate science in decision making. In addition, we have some 20 PhD students located both here in Australia and internationally, particularly in Southeast and Southern Asia. USQ acknowledges the traditional owners of the lands on which we gather. We pay our respects to elders, past, present, and emerging. So our speaker today will be Jacky Croke. Jacky is a professor in the School of Geography at the University College Dublin. Her research interests lie in fluvial geomorphology, environmental change, and landscape response over timescales ranging from the Quaternary 2.5 million years ago to the more recent Anthropocene. Key projects include the Big Flood Project, an Australian Research Council funded project involving industry and research partnerships that defined landscape response to extreme flood events in Southeast Queensland, Australia. She is also involved in a drought and climate adaptation program project, Palaeoclimate for water security using palaeoclimate data to better plan and prepare for extreme floods and droughts in Queensland. I think you will have all read her abstract, so it's my pleasure now to invite Jacky to speak, following which we'll have 15 minutes for the Q&A session. If you have any questions, please enter them into the Q&A on your screen, and I'll hand over now to Jacky. Thanks, Jacky.
Thanks, Catherine, and thanks very much for the invitation to come along and talk to the group today. It's a pleasure to be here. I'll just put this in, yes, slideshow, here we are. As Catherine mentioned, the project that I'm working on, Palaeoclimate for Water Security, it's part of a reasonably large team of us here between Queensland and Ireland and Victoria. It sounds like a rather eclectic combination of people, but I've spent over 30 years actually in Australia working on various projects, as Catherine mentioned some of them there. Perhaps the most relevant is the Big Flood Project, which came into being after the 2011 Queensland floods in the Lockyer Valley and surrounding areas, and I'll put up a link to that website. But first of all, just to acknowledge our collaborators here, John Vitosky from the Queensland Government, Kate Hughes, other people there, SEQ Water, and as Catherine mentioned, this is a DCAP funded project as well, and Ramona Della Posa from formerly DES, but also the Victorian Government, and my collaborators back in Dublin. So by all means, I'm talking today about a large body of work, but tremendous team effort here across continents, really. So the context, I guess, for this work really did start with that 2011 extreme flood event. And I know those of us in Queensland have just been through Queensland and northern New South Wales. In fact, most of Eastern Australia, I guess, has experienced similar scale flooding and inundation just recently. These pictures are of 2011, but I think we could equally put up pictures here of Brisbane and places like Lismore under the current events. And really what that project was about was actually looking at how we quantified the timing and magnitude of those extreme events, in particular, you know, in the context of short records here in Australia. The relevance, obviously, to SEQ Water, who is the largest, you know, Queensland water supply authority, is not just in terms of managing dam storages. We've heard many tales now of major dam storages in both Sydney and indeed Wivenhoe here, other places up north, overspilling. We're constantly concerned about dam overspill and, providing water to a growing population, particularly here in southeast Queensland, which is one of the fastest growing areas in Australia at the moment. But the flip side of that relates to the DCAP work, which is around the better prediction of drought events and indeed the management of these. So it's very much that extreme variability of climate that we associate now with Australia, which represents a real challenge for people, and landholders and stakeholders with respect to water security in general. All of it comes back, and everything I talked about today really comes back to how we quantify that risk. So risk is a function of the likelihood or the probability of these events occurring and indeed their consequences. So looking at that, everything I say today within that risk framework is possibly helpful. Just as a context for this, my colleague Louise Slater from Oxford University published a really interesting article 2 years ago now, actually. I've put the link up there. And she did a global analysis of the changing frequency and duration of rainfall events. And I just thought it was very compelling that really one of the key findings of that work was that, the return period of these large extreme rainfall events are actually changing. So, for example, the former 50-year flood in 1970 now happens on average every 8.5 years. And I think everybody in Australia has this sense, since 2011, we experienced another extreme event here in Brisbane in 2013. We've experienced another one now in 2022, that the frequency and indeed the magnitude of these events is actually seemingly getting closer and closer. Really, one of the problems that we face here in Australia is the length of our gauging record, which in many parts is less than about 100 years if you're lucky. In many cases, it can be as short as 40 years. And one of the most compelling examples that we found of that was actually in 2011, where we wanted to work out the frequency, the duration, the return interval for the 2011 event. And at the time of that event, using 38 years of data, it worked out to be about a 1 in 2,000, 1 in 5,000 actually, extreme event. Now, 2 years later, when we had another extreme event in 2013, we recalculated that return interval and it had dropped to a 1 in 90 years. Now, that's simply a function of changing both the record length, but also most particularly the inclusion of these extreme events in the record. So every time we have a longer record, the probability of including additional extreme flood or drought events actually changes. So we're constantly changing that probability or that likelihood, and that's compelling in itself. So really recognizing that that record is very short, and we understand about Australia's climate being heavily linked even to decadal changes, such as linked to the IPO and other major climate drivers. The big question was, can we extend the length of that record so that we're capturing a much greater degree of that known variability? So the answer is that we do have records. We have what's known as proxy climate records, which are basically a surrogate for climate, often retained in major ecosystems or part of the biosphere. For example, the most familiar one that you might know is tree rings, for example. In the Northern Hemisphere, for example, these records are now routinely used to build up a much longer record, say, of rainfall in many areas. Other aspects that you might, or proxies that you might be familiar with, is ice cores from Antarctica, stalagmites, and cave deposits, foraminifera and sediment. So there's a whole wealth of this proxy data out there that is compiled in global databases, for example, such as NOAA or Pangea. And the question we started with this project is, wouldn't it be great that the water industry had access to this data in a manner that they could actually use? So, the questions that we started with is, where do they access this? In fact, where is it accessed and is it quality assured? It's not as simple as saying to a water industry or a water body authority like SEQ Water, for example, there is this information, where do they get it? which of those proxies are best for a particular climate index, and how can they use that information then in hydrological modeling. So those are the broad three questions that I'm going to try and answer today. Excuse me. With respect to the first one, where is it accessed? Prior to this project, really, there wasn't a standardized database that you could go to that had all the relevant proxy data compiled for the Southern Hemisphere. People like Broma Dixon and Mandy Front had done fantastic jobs at compiling proxy records relevant, high and low resolution proxy records relevant to parts of Australia, but there really wasn't an open access database that people could go have a look at which proxies were available and which ones were most correlated to a particular climate variable. So we set about this. We accessed hundreds of peer-reviewed articles, for example. We wanted to focus really in on the last 2,000 years. The high resolution proxy data sets were our priority. They had to have a link, a pre-existing link to Australian climate, as previously stated, and they had to be fully processed. So we didn't want to include, for example, tree ring data sets that required us to do any additional work. So they were fully processed. Excuse me. So together we put together what's known now as the Palaeowise database. It includes 396 records of paleoclimate for the Southern Hemisphere. The easiest way to review these, because I'm not going to spend too much time on them today, is to hop onto our website, which is listed above there, palaeoclimate.com. And you can go in and interrogate each of those proxy records. It provides the link to the original paper. It provides the lat longs. It provides the resolution and the time span. So that was the first. So that's available on the website. We also wanted to make sure that the database was constructed in a way that it could also be searched by other databases. So it's now, with computing power enhancing, for example, it's now getting more and more common, so that we have global databases of temperature, for example. We've got other databases. So we constructed the database in what's known as the lipid format, or linked information paleodata. And that means that we can update it, but also other researchers can also integrate the database into their compilations. All of that data was published at the end of last year in Nature Scientific Data. The paper title is up there. If you hop onto our website, you will also be able to download that paper directly. So the database is freely available on open access. All of the correlations that I'm going to show you next, the codes to produce those are also available, and we give some illustrations of its application. So we're very happy to see that database published at the end of last year, as it really forms the foundation for the work that I'm going to go on and focus on. So the real question then is, that's the record. We have 396 quality assured proxy records there. Which one of those are best, both for a region or a climate interest, a climate index of interest? So what we did was we focused on 9 climate indices ranging from rainfall, temperature, SPI, which is the standard precipitation index, and SPEI, which is the standard precipitation evapotranspiration index, and various indices of extreme floods and drought. So we extracted these using a silo database for each of the 72 catchments in Queensland over that historic period from 1889 to 29. And we extracted the climate indices at a range of timescales from 12 months to 2 years and so on. And we did that to be able to look at potential lags in the correlation, but also some proxy records may not respond. If we're interested in SPEI, for example, the more extreme droughts that we might be looking at, for example, may not appear for that period, 2 to 3 years, for example. So it's quite a compilation. I'm just going to show a couple of results. This again is available in the paper and on our website as well, but this is just a selection of the correlations between the proxy records and rainfall in this particular case. So the deeper the color there, the higher the correlation. So you can see in the example to the far right of the screen there with the coral example, there's some very high correlations, up to about 75% actually, between the coral proxy and the annual rainfall for selected catchments in Queensland. And you can see the spatial extent demonstrate that that proxy has a large influence really on statewide precipitation. Rainfall. You can also see that others, for example, such as the speleothems, may have more relevance in selected catchments. The same thing with the tree rings. So this provided an indication of, excuse me, which proxies had a good association between rainfall in this case and individual catchments. So this was all done at the catchment scale. This is just a snapshot of the similar output for temperature, for example. And you can see that corals, yet again, are the dominant proxy record here for producing good correlations. In particular, the coral database that Janice Lough was involved with, where coral cores were extracted off the coast of the GBR, the Burdekin and Fitzroy, for example. But you can see, the performance of speleothems or foraminifera in each of these cases was obviously quite poor. So this analysis allowed us to identify which proxies were useful in the reconstruction of the climate index, of interest, whether it was rainfall or temperature. It also allowed us for the first time, I think, to start to see the spatial extent of some of the proxy records. We've never really known to what extent would a coral core from, the Burdekin, for example, apply to other parts. But we can see in that particular instance that there's actually good correlation for a large part of Queensland. So for the database for PaleoWise, what we did was we put that together into a quality assured data set. All of that is open access and freely available now to everybody. We also had a look at the geographic distribution of those proxies. This can be of use to any researchers working in paleoclimate research, for example, because we can start to see the gaps in some of the proxy records available. Queensland is relatively fortunate in that we do have a reasonable density of coral records, for example, but there are many parts of central Queensland and other parts of Australia, for example, that are relatively poor. It also allowed us to quantify, I think, over a large spatial scale, which proxies were best for a given climate variable, and they weren't necessarily the same. In general, the corals perform best for rainfall and variables like SPEI. Other climate indices were also better aligned to tree rings. So corals and tree rings, I think, provided the majority of our correlations. So that was what we produced in that phase of the work, which was a large part of the first DCAP funded project, really, which was the production of that work. The more critical aspect, I guess, right now is how can this information be used? And in order to do that, we wanted to have a look at how those climate indices that we selected, everything from rainfall through to temperature and SPEI, in addition to some of the other major climate drivers that we're familiar with, IPO, Southern Oscillation Index, and other climate drivers that we know have an influence on, that variability in Australia. And what we really wanted to do was to be able to extract these at a level, a time series level, that we could start to characterize it, that we could start to see, minimum and maximum variability. We could start to see if there are any seasonal trends, and in particular that we could start to identify extreme events or multi-year droughts and so on. So this was the second phase of our work, which leads us into PaleoWise R. So PaleoWise was the database. PaleoWise R is the reconstructions as a result of that. So for this work, which was really done with my colleagues back in Dublin, Niamh Cahill and Andrew Parnell, who are excellent Bayesian statistical modelers, we started having a conversation around this, and collaboratively we developed a Bayesian framework. So for those of you not familiar with Bayesian, there's some information coming on our website, but effectively it allows you to use all available information. So previous work in this space may have looked at a single proxy, for example, and its relationship to a given climate variable. What we wanted to say is that, well, we can see that there are good correlations between maybe 10, 15 proxy records here spread across that southern hemisphere. How can we actually mine that information, and how can we develop a framework that builds in the uncertainty both in the proxy records and in the model predictions right from the start? So the Bayesian framework allows you to do that. It's very applicable to a large area. For example, it's, as I said, it can use information from all proxies, and most importantly, for our perspective, it can build in uncertainty. So one of the issues that we face in making predictions, both in terms of past and future climate change, is what's known as the uncertainty around those. And having something that quantifies, 95% confidence intervals really gives the water security industry that greater assurance that, these are the bands that are particularly relevant, that in order to best manage the timing and the magnitude of some of these events, we really should be looking at within that uncertainty and not just focusing on means, for example. And now that we have access to supercomputing, it's a particularly efficient way of generating reconstructions from a large database. So we did that just very briefly. This paper is now in press, and there will be a link. There will be a link in our on our website again. So I'm not going to spend too much time on it because it can get a bit deep. But effectively, what we have is that historical record, which that's our observed historical data, which obviously forms a foundation of some of that variability. We had to characterize this time series distribution for each of those climate variables in each of the catchments of interest. We then wanted to compare the relationship between that proxy and that climate. There has to be a reasonable representation of the proxy climate within that distribution. If there isn't, the model has nothing to constrain itself. So it doesn't, what's known as a convergent test, it doesn't pass a convergence test, and then it's not actually used in the model. Step 3 then is to basically characterize the distribution of both the proxy and the climate with that uncertainty. And there's a whole process where we extract certain numbers of the data set, the time series, to validate. And the final step is obviously the time series reconstruction. So that's roughly what it involves. What we found was using output that was maximized for accuracy, for model accuracy, we've found that the majority of catchments in Queensland produced a reconstruction. So that is, they passed that convergence test and a reconstruction was possible. 2 time steps were evident. One was approximately around 400 or less than 600 years. Other longer time series were up to about 1,000 years. And you can see the distribution in terms of catchments there. One of the things with the coral records, because they're high resolution, they're annual or less in some cases, the time series of the coral records is about 400 years itself. If it's longer, that resolution tends to drop off. So obviously we've identified that corals played a key role in the correlation with some of the climate variables. So that timescale is somewhat constrained by the proxies itself. In other cases, the proxy records may be longer and have higher resolutions. Now, you can optimize the model, not just for accuracy. If you're interested in a longer time series, you can optimize it for that. But as I said, we've optimized here for model accuracy. So that's the best available time series, the most accurate available one. The image to the right just shows you the proxy records that were involved in the Queensland reconstructions. And I've already mentioned the coral records close to the GBI there, but as we extend it out, we can start to see the tree ring records, both from Tasmania and New Zealand, and some of the coral and also sediment cores from Indonesia were also coming into our reconstructions there. In terms of model performance, so each time you have a reconstruction, for example, it produces some sort of model performance, which we've expressed here as a percentage. We'd like that obviously to be within that 95% confidence interval, and the reconstructions for extreme droughts and floods produce that. Overall, the models across all climate variables had a performance of about 79%, which means that the model is accurately predicting it about 79% of the time. So some of them were more accurate than others. As I said, you can optimize for model performance as we've done here and get a shorter record. or you can optimize for model length, and you can determine to what extent that reduction in error actually impacts the application that you're using. So there's going to be a few of these. These are the actual time series reconstructions. So the primary output from PaleoWise are time series reconstructions. The blue at the start there represents the historical data, and the orange lines represents the annual rainfall reconstruction. This here is for the Burdekin catchment over that 1,000 years. It may be difficult to see, but you can also see the standard errors, the standard confidence intervals there, 95% represented. So even looking at this, as a primary data output, we can see that the degree of variability as represented in our historical time period is certainly not fully represented by that longer time series. So we can see considerable higher rainfall values here in that 1300. We can also see considerably lower values represented than that historic period. To us, the time series in itself is tremendously useful. Most of the water industry would say, well, okay, what are we going to do with that? So what we wanted to display is that really, once you have that time series, you can start to look at it in any particular resolution that you want it. So looking at it in terms of a daily, you could disaggregate that into a daily time set for some of the water resource modeling that's been done, and I'll give you an example of that. But you can also start to look at it in terms of, annual resolution, which years were dry, when did extreme droughts occur, when were the dry decades. You can start to look at it in terms of estimating, statistically significant change points over that century timescale. So once you have that time series, to a certain extent, anything is possible. This is an example here of the Brisbane catchments. This is a 1,000-year reconstruction of rainfall for the Brisbane. Again, the blue denoting the historical period there. And we've superimposed on that these grey bars here, which are effectively a drought classification, which was annual, was less than the mean times the standard deviation over 4 consecutive years. So these represent, dry periods over 4 years or greater. And you can start to see the distribution. The red and the blue dots there, which make the graph a bit busy, are really previous work, Anthony Keames and Tozer's work, which have also identified droughts here in Southeast Queensland. So there's some broad alignment, but the main point of this slide is really just to demonstrate that once you have that time series, you can apply a series of, whether it's drought classifications or rainfall anomalies, anything is possible. This is just a similar example really here of using 100-year means to represent the 1,000-year reconstruction we have for the Burdekin catchment. So looking at it over that longer time scale, you can clearly see, again, with our historical period here, how short that is, but we can start to see some of that variability, particularly here in that, early 1800s. But obviously the big outlier here is the rainfall values throughout that sort of 11 to 1200 year time period. So the inset up here is really just some change detection work that we did using the values and their confidence intervals to identify which of those centuries, for example, are significantly different to any others. And you can see that 11 to 1200 period there is very significantly different to anything that we've had, in any time since, and certainly relative to the historic period. What we were also interested in doing was using the database to reconstruct some of the known climate drivers. I've mentioned some of them previously. These are represented here on the Bureau's, Australia climate influences, East Coast lows. We have the El Nino, La Nino, the Indian Ocean. We have the IPO and the influence of the monsoon. And from our early work there with the coral work that I showed you, the high correlation with annual rainfall, we could see that, that there was some potential here to use the database to also look at which one of these proxies may be most relevant to a particular climate driver. So we can start to see, the relevance potentially here of some of the more tropical influences, whereas this one might be the El Nino, La Nino influences that we're seeing in the corals. We can also see others that may be more representative here of the, the Northwest cloud band and so on. To that end, we use the database to actually also reconstruct the 1,000-year time series for each of those climate drivers now. So this is the IPO 1,000-year reconstruction. Again, the historic, the documented one there in blue, and our own reconstruction in orange there with uncertainty. And we did this for SOI. I'm not going to show it, but we also did this for IOD, NN3, 4, and so on. So we have now a 1,000-year time series for each of those major climate drivers. So our intention is, sorry, this is a very busy slide, but we're working on a way to actually show, so the top sequence there shows you the percentage difference of annual rainfall relative to the present, for example. So anything that appears very red was considerably wetter, maybe 50, 75% wetter than the historical period. We can see the performance of individual catchments throughout that. Underneath here are the time series for the climate indices, and we're working on this at the moment for a graphic where we attribute each of the changes in rainfall, or SPEI, to a dominant climate driver. So in some cases that might be IPO, in other cases it might be IOD, and so on. So when this work is finished, we'll have not just a visualization of the percentage changes in rainfall relative to that historical period, but which of those climate drivers appears to have been the dominant attribution. So that was a very quick overview. I appreciate that. I'm hoping I leave enough time for questions, but effectively those time series can be used in any number of ways, really. And we're very keen that people appreciate that. It can be used in heat wave analysis, bushfire frequency, land suitability, obviously future climate analyses, habitat and coral bleaching. Once you have that time series, you can start looking at these changes in a number of key aspects that are now very, very relevant to Australia's future adaptation to a warming climate. What I want to focus on today is just some very brief applications to water security planning. So obviously, as I said, SEQ Water are, the major bulk water supply authority here. They're completely responsible for the supply of both our drinking water, but also water for irrigation, supporting agriculture. So one way that they would use these reconstructions is in their rainfall runoff models and their water resource assessment models. So this is work that John Vitosky has done, who does this work for SEQ Water anyway. This allows you to look at things like dam volumes, but also drought occurrence and, spills and so on. So how can we use this information to better predict, droughts and flood frequency? Can they help with things like, water level restrictions? And how do they actually help with planning for water supply scenarios? Obviously, DCAP, as Catherine mentioned, one of their major areas is around drought predictions. We've obviously had several major droughts now in Australia in general, the Millennium, the Federation drought, which really just highlighted how vulnerable. But large parts of Queensland are almost permanently in drought. Prior to the recent rain in 2022, SEQ Water's major dam storage, Wivenhoe, was sitting at around 36%. So we are completely aware of the vulnerability in this space. So what John did was he did a simulation model using his water resource model. I think it was a combination of Sacramento in this case, and he actually tried to quantify the dam inflow for those two particular droughts, the Federation that we have here, you can see, and the Millennium. And you can see just basically the slightly different sort of drawdown characteristics of those two droughts. But the main purpose here was that we would get an estimate of the volume of water that was characterized with that, which turned out to be about 450,000 megalitres. So we've estimated that a severe drought would actually occur at around that threshold. So what John was able to do then was he ran two scenarios. So on the left of the screen here, you'll see what's known as the static climate model. There's no variability. This is the prediction here for the inflow, about 450,000 using just the observed record. So it sits at about 1%. If we use the entire record, the 1,000-year reconstruction, that increases to about 2.5%. But you can see that the impact of that static climate model is there's very little variability in the centuries throughout that. If you look at the paleoclimate time series that John ran, this is the observation prediction here, but you can see for over the timescale, over that 1,000-year timescale, the probability, which is annual exceedance probability, has increased from about 1% to 5%. The advantage as well is that we can actually look at the performance, for example, in that 1700, you can see that the probability is actually increased to maybe about 10 or 12%. So for SEQ water, rather than looking at a standard estimate of the probability of, say, a millennium type drought sitting at around 1%, we can actually sort of inform them that in fact the probability of that is much greater. It has increased with that 1,000-year record to 5%, but it can be up to 10 or 12% if you experience a century like we did previously. All of these outputs are really just to demonstrate the difference between using the observational period alone versus using that longer time series. This here is annual inflow into Wivenhoe Dam, for example, and each of these boxes, which are sitting above the blue boxes over the so Wivenhoe is a multi-year storage dam, you can see that the probability of that particular inflow over that timescale is always higher. So even at the 10-year timescale, but importantly, when we're using water over that 5 to 6 year timescale storage times, we can see that the probability of that inflow reducing is always significantly higher than just using the observational data set alone. The other area that SEQ water are particularly interested in is the setting of medium level water restrictions. Many of us living in Queensland are very familiar with when these kick in, but to a certain extent, using that longer time series, so the same output here, for example, using the static climate model and the observational period, medium level water restrictions are a very low probability. If we start looking at the longer time series, we can see that that probability is actually increased, from about 4 to 8%. And we can start to see some of the variability in some of those centuries. So in terms of them managing the timing and the the preparation, the preparedness for these sorts of events, by showing them the impact of some of that longer time series data, they can start to better inform. They can start to make more informed decisions around at what point would they kick in. Other aspects would be, as I said, the mean annual inflow. Again, this is a simulation using the water resource model that John did, and we can start to see that because that reconstruction period was overall, it was actually quite a dry period, the probability there, the inflow is actually reduced significantly in some cases here, but over that time period of the aggregation period. And what this informs SEQ water is that obviously relying on these estimates, just using the historic data, obviously operating within these 95% confidence intervals would allow them to better manage the risk of drought. And the same analysis can be applied to dam overspilling, irrespective of the output here. The whole logic is the same. Once you have an observation period of 100 years, once we change that to 1,000 years, we can start to see fairly significant changes actually in the probability of an event, whether it is a drought or a water restriction or a dam overspill actually occurring. One of the things that people have asked us is, coming back to the extreme flood events, to what extent can the time series actually accurately predict the magnitude of these? So the time series, as I've shown you, can identify, periods. For example, here we have the Fitzroy catchment. This is the time series. We can clearly see that there have been years where the rainfall estimates have been, several, orders of magnitude, well, not orders of magnitude, but much, much higher than we observed in the observational period. In fact, for this record, there are at least 25 years in the Fitzroy where we experienced rainfall that was beyond that ever recorded in the historical period. So we do know that there's been some more extreme flood events. In terms of using these time series to predict magnitude, we would advise against it simply because the resolution just isn't there. It's what we demonstrated in the Big Flood project was that you can use a different technique, paleoflood reconstruction, which is now well established globally, but Darrell Lamb in his PhD as part of that project demonstrated that the degree of uncertainty around just using the gauge data for the prediction of these extreme events was considerably high. As soon as you added in the historical, that reduced somewhat. But basically, as soon as you started to add some paleoflood data in there, which very specifically measures flood magnitude in addition to timing, you can actually reduce that uncertainty by anywhere up to 60 or 70%. This is not a very complicated or indeed costly approach. So we would certainly advocate if particular stakeholders were interested in, the detail of elevation of flood magnitudes and so on, that this would be the approach. If you're just interested in using rainfall to run your water resource model and looking at that, that's a different application. So we're very happy to see that work included now in the Australian Rainfall and Runoff updated versions, where it is recommended that paleoflood analysis can be used in the prediction in the intensity, frequency, duration predictions here in Australia. So that was a bit of a whirlwind. Really, everything that we've talked about here is hoping that these data sets can actually assist everybody. There's a vast range of stakeholders that are engaged, both in risk and disaster management. This aspect of living with uncertainty, there's been a lot of conversation really following the events in 2022. How prepared are we? Should we putting our communities at risk of some of these extreme flood events, and what can we do better? So we're very keen in this project to make sure that the information is reaching as many of those stakeholders as possible, and we'll be producing a series of infographics demonstrating some of the potential of the time series to help in some of that sort of climate adaptation work. So just to wrap up, I gave you a brief introduction to the PaleoWise database that's freely available now on our website. PaleoWise-R is the approach that we use to reconstruct climate variables of interest. In addition, we used it to reconstruct major climate drivers of interest using SOI, IPO, and the IOD, for example. I've demonstrated a couple of the primary outputs in terms of the time series plots and some of the things that you can do. Obviously, the specific application of the time series or any derivatives is really user dependent. So we can't produce a definitive application here because, in all honesty, every potential user would have a different need. It would be trying to answer a particular question, for example. So really it's up to the individual user, but we've done our best to ensure that the data is as freely available as possible. So as I said, the Palaeoclimate for Water Security website has all of the information that I've talked about this morning. There's also the opportunity to sign up to our newsletter so that when new editions are added to the website or we publish any new papers, that's also available. So feel free to hop on there. And hopefully I've left enough time to answer some questions, but thank you very much. I'm hoping that that overview, as rapid as it was, gives you some indication really of the potential and indeed the enormous value that these data sets hopefully will have to future predictions. So I might leave it there and see if there's any questions. I'll stop sharing my screen.
Thank you, Jackie. Do we have any questions? None currently listed in the Q&A. That's okay. I guess just listening to you, so obviously there's a good relationship for rainfall. Do you find relationships also for temperature and particularly sea surface temperatures? I thought that might be.
Yeah, to be honest, Catherine, we haven't really, given the size of the database and what we were actually sort of
your focus.
Yeah, we had to narrow it. I put it out there. If anybody is interested in looking at the temperature database in particular, we would certainly welcome that collaboration. But at this point, the reconstructions are there, but we haven't really focused on them in any way that I could give you any further insights. We've really focused now, given the emphasis on floods and droughts, we focused on rainfall, SPEI, in any of those other derivatives, you know, the extreme floods and droughts. Otherwise, it was pretty overwhelming.
Yeah, absolutely. Does anyone in the room have a question? Louis does a lot of crop modelling. You might be able to incorporate some of that into the.
Yeah, I guess that's one of the potential applications that we're hoping is that people, you know, may see the application of some of the time series into crop modelling. Spoken with some of the collaborators at DES, for example, that do this, John Carter and others. Again, it would be great to see the
crop modelling and the pasture modelling.
Pasture modelling, yeah, that's right.
Would be, you know, it would be very useful, but especially those periods when, you know, if it is likely that we might see some of those higher rainfall events again.
Absolutely, yeah, that's right. And I guess these are all conservative estimates, really, which I guess in some respects is potentially alarming for us, but nonetheless they are conservative because, of course, we don't really have you know, urban or human influences to a certain extent as we have in that historic period as much. So yeah.
Hand over to Christina.
Hi Jackie, thanks for a great talk. It was really interesting. I was wondering, I'm not working in this area, so pardon my naivety, I guess. But I was just wondering, like I read that for the 22 floods that we just had. So similarly, like the data was there, but the governments are not taking it on board and using it to, you know, warn the people properly and in advance. So I saw that, yeah, the predictions were like a month or two before those, like the recent floods for Queensland, but it was just not acted upon. I know it's probably beyond the scope of your research, but I just thought, what's your thoughts in terms of how can we get the governments to use that data like more efficiently to actually have our own ground, you know, benefit for people?
Yeah, it's a big question, isn't it, really? I mean, I think Australia's focus has been to really fund you know, flood cleanup, flood recovery, really. That's where the investment, the financial investment has been. I think there's probably been much less gone into flood warning and, you know, flood communication. And I know, you know, many people here in Brisbane were very disappointed with the absence of any warning really around those floods, particularly in some of the upper creeks. And that came out of 2011 very clear as well. There simply wasn't the infrastructure in place to be able to communicate that. You know, I guess one of my personal frustrations is, having worked in this space a little bit, is that there is a disconnect between each of the authorities, really. And when we might produce this information, but even getting it into, you know, fairly obvious users like SEQ Water or you know, the Bureau, for example, that's a major challenge, because really the incentive to do that is very little from their perspective, really. I don't know whether that's going to change. I hope it will. I think the frequency that we're going to experience these floods may well change the focus of, you know, sort of clean up to, you know, better predictions. In my case, why wouldn't people use that data set? If we're going to, you know, if we're going to stress test both our infrastructure, but also where people are living, why wouldn't we use a longer time series that actually has uncertainties quantified? Like if I'm a person living on a floodplain, I would like to know, you know, within the confidence intervals, am I going to be flooded every, you know, year now or 10 years and so on. So, and we can see from some of the output that I showed you, just using that observational period effectively shows no variability. They're not modeling change. They're not modeling for change. When we look at the longer time series, we can see that there has been significant variability, even outside of, you know, more recent climate change, for example, and how prepared are we for that? And I would argue probably, you know, we need to be focusing better on that, capturing that variability.
Thank you. Jacky, what was the response of SEQ Water? I mean, you've spoken about the modelling in terms of how it informs drought, water management, you know, heading towards drought, and the introduction of restrictions. But when you showed them the reconstructed data that showed these more extreme rainfall events.
Yeah, I mean, to be fair, SEQ Water are, they've been a very good supporter of this work, I have to say. They've invested in it, and they invested in the big flood event as well, in terms of generating that research understanding around these extreme events. I think, obviously everything is it's a reactive space, so it's about giving people time. I've now concluded that this isn't going to happen overnight. It's going to be a case of, trying to maintain awareness of the data sets, and, hopefully those collaborations between the water modelers. John Witowski does all the water modeling for SEQ Water. So John's been a collaborator on this project, and that's been enormously valuable for us, because John can see what are the applications, what are the limitations, what sort of resolution do you need to be able to do the sort of scenarios that John would do for them. So I think that's been hugely beneficial, and that's been a huge win for the project, is just having that collaboration. So I think it's hard, and as you would know, I guess, from my perspective as researchers on the project, a project has a start and an end date. Unfortunately, this project is now ending. The extent to which we'll get future funding to keep, raising awareness or keep, collaborating is very uncertain in this space as well. So it's definitely at both ends of that spectrum, I think.
I imagine there's a little concern though about whether the current infrastructure, which is based on the recent historical inflows, how that would cope in those situations, given the challenges already that we've experienced with extreme rainfall events that we have experienced recently. Yeah,
I mean, SEQ Water would be modelling there for PMF. They would be modelling basically for very high extreme events anyway, like a 1 in 1,000. I think, as I demonstrated in my third slide, is to what extent these 1 in 1,000, 1 in 5,000, really that's the crux of the problem. They are managing for extreme events, but if we can go from a 1 in 5,000 to a 1 in 90, just basically in 2 years, I think really that's fundamentally what the problem is. So they are aware of it. It's not that they're not managing that risk.
No, it's obviously a challenge.
Yeah, no, definitely. It is a challenge for them. And really, the only way that we can extend that record is through paleoclimate data. We don't have another way. And I guess it's always been a little bit confusing for me why, a lot of people talk to me about accuracy and uncertainty, when in fact, the historical record that we have is not accurate. It's recorded, it's not accurate. But there is sort of a lot of focus really on uncertainty. That's why we went with the Bayesian approach, because the uncertainty is modeled into those reconstructions. So, sure, there is uncertainty, and you can see that once you go past 1600, for example, that uncertainty actually increases. But the extent to which that influences the output from a water resource model, it's marginal. It really is, relative to that historic period, because, do we genuinely feel that, the data that we captured in 2022 is accurate? I mean, we've recorded it, but it's certainly not accurate. Most of the gauges would have been lost, I suspect. But so, yeah, it's about the communication of some of that perception, I think. So,
are you involved in similar work in Europe? Because there's been serious flooding.
Yeah, definitely. I'm involved in a couple of projects, a Water Futures project there that's looking at it. Big investment in Europe into this space. I mean, paleoclimate data is more routinely used anyway over there, I would have to say, just because of, say, tree rings, they have greater confidence in the annual resolution of that. It's taken Australia quite a while to sort of come on board with some of that data sets. And the flood work in particular, both the US and Europe now are using paleoflood data routinely in the calculation of these extreme events. So I think Australia really needs to sort of just embrace it, really, would be my approach, because, we're not really going to gain any advantage by sitting on the sidelines debating accuracy and things like that. We just have to use whatever we can, because climate is changing, as we know.
Yeah, absolutely. No other questions from anyone in the audience? So I think at that, we might leave it there, Jacky. Thank you very much.
No worries.
Very much appreciate your time and fascinating talk. Thank you.
Okay, thanks very much for the opportunity. Thank you. Bye-bye.
Thank you. And thanks everyone for joining us.